I don't blame you. I was looking at the schedule and I was going to drag out functions over 2 days, but we actually could do it in 1 day. So I'm tempted to do that. And then we wouldn't have a class on the very last day of classes. How about that? We'll see. Exciting. I know what you're thinking. Well, are you going to cut our final exam review? No, we would do it on the Monday instead. Okay. I was so excited about my question bank. I forgot to change the label. Sorry about that. Because I'm developing this beautiful question bank. And I'm very proud of it. Doesn't mean anything to you, but source of pride. Okay, so pulls LaTeX files from all different locations. It's pretty snazzy, pretty snazzy. All right. I give you a list of core concepts. Now, a lot of the stuff that's on this test is just from our notes, so not in the textbook. And so that's why it just says notes here. And just kind of, these are all the things that we did, right? And so some of these concepts are kind of tested in a big question, right? So for example, if we're talking about linear equations, graphing a linear equation, graphing a linear inequality, sketch the feasible set and find the intersection of the lines, that would be kind of all in one question, right? And so all those things would be tested in one question. But let's see here. You'll have the formula sheet. That's what I wanted to find the formula sheet for. Oops. But it's the same as test one. So the only new stuff is the exponents and logs and potentially the quadratic formula, which came in handy for some of those exponent and log questions that we solved, right? When you have an x squared or something in there that you want to solve for. But besides that, the next ones are just logic, which we didn't even use. And I guess you could look at the Boolean algebra, but I think matrix algebra for Boolean is kind of relatively easy and you don't need the laws. Okay. How do you want to do this? Should I go through the core concepts or just get into the questions? And is there any particular question that you want me to start with, or should we just go start to finish? Start to finish. All right, let's do it. Let's do it. Should I go through the core concepts? Got it. So exponents and logs, you've got the laws of exponents, right? How do you merge things of the same base, for example? What's allowed, what's not? Exponential functions when the x is in the power, right? Logarithmic functions when you have a log, of course. You have to know the domain of exponential functions is all real numbers, but the logarithmic functions, let's just remember that if you have the log of x, if f of x is the log of x, then x has to be greater than 0, right? I can't take the log of a negative number or 0. I should say nor 0, right? And I am pretty sure I started, but this would be a really bad recording to miss. Okay, good. For me. Properties of logs. Those are those log laws that are on your formula sheet, right? So being able to combine and expand logs, right, into bigger logs or kind of squish them up into a single log. Same thing, use it for exponents, right? solve for a variable inside a logarithm, which we called logarithmic equations, of course, and then solve for a variable in the exponent. That's an exponential equation. And I want you to keep an eye out for quadratic equations, right? Because then you would use x, or I guess a quadratic equation, let's start there, is something like ax squared plus bx plus c is equal to 0. You can solve by x is negative b plus minus the square root of b squared minus 4ac over 2a, which, in case you don't have it memorized, is on your formula sheet, but maybe you do. Or a quick Google away, your calculator can probably do it as well. Right? And I don't really care, as long as you show me that that this is what you would use, right? You can plug through and find the values, or you can just say, I use my calculator, here are the answers. Either way, it's fine. Might be worth a Google. All right. Then we moved into linear equations and inequalities. Right? We graphed a linear equation. What do you need to graph a linear equation? You need 2 points on the line. You can plug in any value of x and solve for the y. And then again, any value of x and solve for the y. I try to pick convenient values of x and y, but it doesn't really matter. Graphing it, I won't get you to graph it. What I will do, so on this practice, I get you to graph it. But what you'll find is that it's pretty time consuming, and that's not really what this is about. And so what I'll have is I'll just have the lines on there, and you need to tell me which one represents which equation. All right. So still kind of have the skills, but you don't need to actually draw the lines. I'll draw the lines for you. Okay. Sketch the feasible set of a system of inequalities, right? This is, like I said, these guys are all in, let's see, what question was it? See, question 6. All those things are tested in one question, and that's why I like it. Right. Whenever I can test multiple things with one question, that's a good question for me. If I give you 2 points on a line, you have to find the equation of the line. How are you going to do that? You have to find the slope first, and then use one of the 2 points to find the intercept, right? And then you'll have the equation of the line. Find the equation of a line parallel or perpendicular to a line through a given point, right? What does it mean to be parallel? It means that the slope of the first line is the same as the slope of the second line. Okay? That's not on your formula sheet, right? Neither is this. M2, if they're perpendicular, the second slope is going to be -1 over M1. That one might be a little bit trickier to remember, but M1 times M2 has to be -1. So you have to memorize those, I guess. This is a practice for the test, and so I have questions for each of these. It'll just be one of them, though. But you have to be prepared for both. Solving an absolute value function, right? The inside can be the negative version or the positive version, so there are always 2 answers for the absolute value function. An absolute value inequality, right? Depending on kind of how comfortable you are with the graph of the absolute value function, right? Or you might need to use some test points to figure out where the inequality is true. And then I won't test this, but it is something we introduced in this section, because then we do systems of linear equations as a whole other section. So felt like overkill, but you can solve a system of equations either by substitution or elimination, right? If you have 2x plus 3y is 14 and 14x minus 2y is 13 or something like that, then you can solve for x in one and plug it into the other and solve for the y, and then you can plug it back in, right? That kind of thing. But we developed a quicker way of solving those using matrices, right? And so you can use it by substitution, but I'm not going to test you on substitution or elimination. We were just building up to the next section, which is systems of linear equations. We introduced the elementary row operations, which are you're allowed to swap rows, you can multiply by any constant, and you can add or subtract any multiple of one row to the other, right? Just 3 row operations. The augmented matrix, I can't remember if we called it the augmented matrix. I'm sure we did, because where else would I get this terminology from? But let's see here. The augmented matrix is one that looks like this, where you have kind of XY, XY, and then the line, and then the solution 1, solution 2. Augmented in the sense that the solutions have been tacked on to the matrix. Gauss-Jordan elimination method to solve a system of linear equations, right? That's where we turned the first entry into a 1, and then we pivoted, right? And then eliminated all the values below it, turned them into 0, right? And then we moved on and worked through it until we had the diagonal, right, of 1s. What does it mean to have no solutions? To have no solutions, we have no solutions. No solutions if we end at a false statement. Something like, or I guess it should be e.g. For example, something like 0, 0, 3 equals 0. No, oh my gosh. 0, 0, I did it again. There. That's a false statement. Because 0 times x plus 0 times x times 0, or plus 0 times z, ugh, can't talk today, can never equal 3, right? So that's false. Which is the same problem, anyways, whatever. Infinite solutions is when the statement is always true. 0, 0, 0, 0, for example. That's always true. True for all x, y, z, for example. Giving it infinite solutions. Should change the color on this. There. Darker. Okay. Then we moved into matrix algebra. We added matrices, that was nice. Well, first we had to, I guess we technically had to introduce the order of matrices, which is m by n, the number of rows by the number of columns. But I wouldn't even say that's you just have to know that, right? The order of the matrices determines whether you can add matrices together. What do you need for them to be able to add together? They have to be the same order, right? Because they have to match up. Scalar multiplication. Scalar multiplication, just to clarify, is something like A times the matrix B, where A is just the number. And it behaves the way we want it to, right? Because it just does what? Just multiplies every item in the matrix B by a lowercase a. And so it's just multiplied. And I guess I should clarify here, adding matrices A time, which is m by n, plus B times is m by n. So they have to be the same order is what that means. What about multiplying matrices? That's tricky, but do you think it's kind of fun too, a little bit? It's kind of fun. No, it's where you have to take the row and the column and you have to lay it on top and multiply the values and then add them all up to get to the entry. And then you do it n by n times. Let's see here, multiplying matrices. What's the rule for multiplying matrices? Let's focus on the order of the matrix. They have to have matching columns, columns to rows, right? They have to kind of match up on the inside of the orders. Okay? So A can be m by n, but then B has to be n by P, let's say. Doesn't have to be LMN O, but that's weird to use an O, so use P. But they have to match up here. What's the size of the resulting matrix? C would be m by P. From here. Right. So they have to match up. The number of columns in the first one has to match the number of rows in the second one. Otherwise, they won't lay on top of each other nicely. And then the inverse of the matrix. The inverse of the matrix, we did look at the determinant, and you're welcome to memorize the determinant, but that's just for a 2x2 matrix, right? So that's kind of limiting. But what did we say? We said, okay, well, to find the inverse of A, let's say, we can tack on the identity matrix of the same size. And then we can morph matrix A into the identity matrix, but in doing so, this side of the augmented matrix is going to turn into the inverse of A. So as you move this and turn it into the identity matrix, then this side becomes the inverse, which is kind of, I think, the easiest way to do it. Obviously, if you don't have software. With software, it's very easy, but we don't. Not here, at least. Okay. Last section, relations. There's a lot of bullets here, but they're all just definitions, so it's not too bad. Relations are what we did last day. The directed graphs, right? A graph of the relation. We also mapped the relation using at the adjacency matrix, right? What does it mean to be reflexive? It's going to be reflexive if all the nodes have self loops. So here, all nodes or vertices, whatever you want to call them, vertices have self loops. What does it mean to be anti-symmetric? Well, let's talk about symmetric first. That's transitivity. Getting ahead of yourself. Symmetric relations is if you have a trip from A to B possible, then you need to have a symmetric trip B to A. And so we need to have kind of return trips. You can talk about it in terms of flights. And so if there is a one-way, we must have both ways. If there isn't one, then you don't need to replicate it. But if there is a one-way trip, then you need to have the trip back as well, which is easier to see if you have the graph, right? Then you can just look and see. Anti-symmetric is if there is a one-way, then there cannot be a trip back, right? There can only be one edge. Only one edge or arc, we called it. It's just so if you have something like 1, 2, 3, this relation, and it looks like this, let me do a different color, then this is an edge or an arc. And so let's see here. Here I can go from 2 to 1, or I can go from 2 to 3, which is anti-symmetric. How do I make it symmetric? Yep. And I would need a trip from 3 to 2. Yeah, so that's getting into the transitivity. But the symmetry has to do with those specific trips, right? That would be a layover. And that's the transitivity. So a transitive relation is if you can go from, just like you said, from 1 to 3 to 2, I need to also just be able to get there with a direct flight from 1 to 2. And so here, transitive, if AB and BC, then AC must exist. Am I writing too small? I usually write bigger.
I was in the back of the room, so it's probably writing a tiny bit smaller than usual.
I think so.
But I was in the back of the room.
That's fair. I'll write bigger for the questions. It's just this page, I didn't give myself very much room. Okay. Then the definitions. A partial ordering, and I have to cheat because I don't have a test coming up, so I don't have to memorize it. I will though. Is when it's reflexive, anti-symmetric, and transitive. So if it is all those three things, we call it a partial ordering. And that's just definitions. Slightly different. What is, maybe I'll use big again. What's an equivalence relation? It's reflexive. And I'm going to use those little ditto signs because the only thing that changes is the symmetric, making it slightly easier to memorize. Again, just a definition. To kind of special cases. Boolean arithmetic for matrices. Boolean arithmetic is so nice, right? If you see a 1, you have a 1. And if you see all zeros, you have a 0. Fair enough. But we use it for matrices, especially. I didn't introduce the term closure, and I don't know how I managed to do that. I think because they don't use it in the textbook, but then all the questions that I have talk about the closure. Okay, and so the closure with respect to these things, reflexivity, which I have a hard time saying, symmetry and transitivity, would be what relations are missing in order to make it reflexive, in order to make it symmetric, and in order to make it transitive. These two are easy, right? You can, if you are able to draw the relationship, then it's easy to see what ones are missing, right? It's the transitivity, but we did talk about the closure of the transitivity is going to be that S plus or R plus or whatever, but we introduced it as S plus, which is what the closure with respect to WRT with respect to transitivity of some, I'll do this, relation of R on A, where A, the cardinality of A, let's say, is N, generically. Okay. Where, and R is the adjacency matrix. Oops, matrix of the relation R. What we can do is you would find that S plus, which is the closure with respect to transitivity, so all the links, including the original relation. And technically, the closure includes the original relation as well. And so is going to be R plus R squared plus R to the 3 plus all the way up to R to the power of N. These are matrices each. How do you get R squared? You take R times R. Matrix multiplication. Uh-oh. How do you get to R to the 3? Well, you take R squared times R. And then you take it times R all the way up until N, which is going to be the set size of A. Right? So if, for example, A has 4 elements, 1, 2, 3, 4, then you would have to go up to R to the power of 4. And then you add all those matrices. Right? Kind of sneaky. But what if I just make A have like 3 elements? That's not so bad. That's a good exercise. Right. Then it would just go to here. You have R already. You'd need to find R times R, and then take that times R to find R to the 3, and then add those all up, right? And so then you're adding matrices of the same size. And they would be square matrices all throughout. And that's all you need to know. Are there any of those topics, now I should ask, that you want me to start with? Or just go from the beginning, top to bottom? All right, here we go. 4 to the 3 over 2 is equal to 8. Well, on your formula sheet, you have that, where is it? If a to the y is equal to x, then log base a of x is equal to y. That's why it's only 1 mark, because all you have to do is track these. A is 4, so log base 4 of 8 is equal to 3 over 2. And you can confirm it by taking 4 to the 3 over 2, so that's your first step, should equal 8, that's your second step. Been a while since we did logs. What if you have to solve log base x of 729 is equal to 6? So I would use this formula again. Okay. Log base x of 729 is equal to 6, but map that back to here. You would get something like x to the power of 6 is 729. I can undo that and get to the x by taking the 6th root. It's an even root though. Oops. So you add on the plus minus, 6th root of 729. Which I'm good if you leave it there, but I'm pretty sure I did it and it works out to 3, so that's kind of nice. But you don't have to. How would you find, if you don't have a fancy calculator, which you don't have to, how would you find the 6th root of 729? 729 to the 1 over 6. Right, and then plus minus, I guess I shouldn't circle the plus minus. Oh. So you don't need to have a fancy calculator. Got the skills. All right. And I can't remember if it's on your formula sheet. That probably. Making you work for it is not. That's okay. You don't need it. What if you have to solve the log of 2x plus 6 is equal to 5? How do you get at something inside the log? You would raise both sides to the same base. All right, this is log base 10, so I'm going to go for 10 to the log of 2x plus 6 is 10 to the 5. You don't want to forget about the 10 to the 5, right? It has to be to both sides. But once you've done that, then the 10 to the log base 10 is going to cancel by the log laws on your formula sheet. And so 2x plus 6 is 10 to the 5. Which, if you do a little bit of math, 10 to the 5 is huge, and then you subtract 6 and you divide by 2. 2x is 10 to the 5 minus 6. So x is 10 to the 5 minus 6 divided by 2, which I'll squeeze on here. 49,997 works out. I'm fine if you stop here. As long as you rearranged for x, that's fine. It works out to a nice number, but don't have to. And then I am going to change this to be 4 marks instead. So here, these are the marks roughly. Obviously, this is kind of a draft, and so I do make adjustments as I go, but just to give you an idea of how much time to focus on things. Okay, if I want to solve this, I've got log base 2 and log base 2, and that's good because then I can look at maybe combining these things. If I'm adding the logs of the same base from your formula sheet, right, then you're multiplying inside. And so this becomes log base 2 of x times x minus 2. Nothing changed on the right-hand side, right? Then, because I can't solve for the x, I can't raise it to the power of, or 2 to the power of the log base 2 until I have it as 1 log. And I wonder, I'm thinking about that one problem. Anyways, log base 2, 2 to the log base 2 of x squared minus 2x is 2 to the power of 1. Which tells me x squared minus 2x is equal to 2. But I want to solve for x. So I got to keep going. But here, what did I say in the core concepts? Keep an eye out for quadratics. This is a quadratic. X squared minus 2x minus 2 is equal to 0. Right? So let's go here. Here, this is a quadratic. And can I do it over here maybe? I get x squared minus 2x minus 2 is equal to 0. Has to be equal to 0, right? Otherwise the quadratic formula isn't going to work. And like I said, you can try finding a way to do it on your calculator, but it's not too bad. X is negative b plus minus the square root of b squared minus 4ac over 2a. B is negative 2. So x is negative 2 plus minus the square root of negative 2 squared minus 4 times 1 times negative 2 over 2 times 1. Working with the square root, inside the square root here, I get 4 minus 4 times negative 2. So 4 plus 8 is 12, root 12. If you want to just use your calculator, that's fine. But we can cancel a little bit or simplify a little bit. We get 2 plus minus, and then the root of 4 times 3 divided by 2, because then I can float that root of 4 outside and get 2 plus minus 2 root 3 divided by 2, but this is all going to go to 1. So then x is 1 plus minus root 3. But wait, there's more. Hence the adjustment to 4 marks. I don't know where I was at with 2 marks. Yikes. What is more? 1 plus root 3 is fine if you try it. 1 plus root 3. One plus root 3 is roughly 2.732. But 1 minus root 3, what's the problem? Negative 0.732. I guess I could toss a 1 on there. Why? Because my domain, right? I can't take the log, and here what's nice is I have just the log of x, and so I can compare it to x, and I have x minus 2. So this one can handle a larger value of x than this one can. And so this is our limiting factor. So then x has to be greater than 0. Well, here, x minus 2, let's see, I'll do a different color actually. And x minus 2 has to be greater than 0, but that means x has to be greater than 2. Okay, so I guess that is, nope, okay, yeah. All good. So that's the limiting factor. 2 is x has to be greater than 2, because x has to be greater than 0. Whoops. It doesn't say explain. If it said explain, I would say, yeah. But I would say, therefore, x is equal to 2.7321, or 1 plus root 3. And then just indicate that this one is not a solution. Oh, I did some things. I did 4 plus 8 is 12, but then I rewrote 12 as 4 times 3, because then I can distribute the square root onto the root of 4 and then the root times the root of 3. But that was just a sneaky way to ditch some of these 2's, right? Be able to cancel. You can just leave it as 2 plus minus root 12 over 2, but you'd get to the same answer. So that's fine. Yeah. I guess I was just showing off at this point. No, I just don't like to deal with the denominator, that's all. So if I can ditch it, I will, but you don't have to. But you do need to tell me that there's only one solution, not 2. Okay. From here. It's a lot of arrows on here. And don't worry, I've made a note to give you more space for this one. Okay. Any other questions about that one? Okay. Solve the exponential equation. So now we're solving for x in the power. First thing we need to do is we need to isolate that exponential equation, right? Which means I need to move that -2 over to the right-hand side. And so I get 3 to the 2x minus 1 is -4 divided by -2. 3 to the 2x minus 1 is 2. choose your own adventure, but to grab the exponent, you're going to need a log, any log. You could use the natural log, or you could use log base 3. Those would be probably my go-tos, or log base 10, I guess. But it doesn't matter, the results will be the same because the log laws are all the same. So should we use log base 3 or log base E? Natural log is nicer to write. No? Log base 3 of 3 to the 2x minus 1 is the same as log base 3 of 2, or is equal to. We used the base of 3 because we had a base of 3 in the exponent, in the exponential function. But now those log laws let me bring down the 2x minus 1. Technically, it's multiplying log 3 of 3, which is equal to 1. But we don't write that typically. Is equal to log base 3 of 2. Log base 3 of 2 is just a number. It's just the exact form of a number, just like a fraction would be. And so now I can just rearrange everything and solve for x. And so I get 2x is the log base 3 of 2 plus 1. So x must be the log base 3 of 2 plus 1 divided by 2. And I would just leave it there. You don't have to figure out what that is. No, because there's no restrictions on the domain of the x, and so it'll just take any value of x. How about versus using the natural log? Just to show you that they're the same. So if I take the natural log of 3 to the 2x minus 1 is equal to the natural log of 2, I get 2x minus 1 times the log of 3 is equal to the log of 2, the natural log of 2. Remember, there's only one log for me. It's the natural log. So I just call it the log. It's bad. But natural log of 2 and the natural log of 3, they're just numbers. And so 2x minus 1 is the natural log of 2 divided by the natural log of 3. From here, we can use the change of base formula, which is on your formula sheet. If you have log base E of 2 over log base E of 3, then you have 2 logs of the same base, C, B. You can rewrite it as log base B of C. So log base 3 of 2. Ta-da! Wow. By the change of base formula. And then you're back to here. So it doesn't matter which log you use. In fact, you can just leave it as the log base E. You don't have to convert it. I just wanted to show you that they're the same. Nice. Any questions about that one? Graph the feasible set of the system of inequalities and give the coordinates of the intersections, including the x-axis and the y-axis. Whew. Okay. This is where I said, okay, I'll be nice and I'll draw the lines for you, but you'll have to tell me which line corresponds to which equation. So first thing we're going to do is we're going to label these and say 1, 2, 3. and then x greater than 0, y greater than 0, x greater than 0, let's just tackle those right away. Tell me that x has to be greater than 0, so I have to be on that side in my feasible set, and y has to be, oh, sorry, I said those backwards. X has to be greater than 0, so I have to be on this side of the y-axis, and y has to be greater than 0, so I have to be on this side of the x-axis. Which is why I only gave you this quadrant anyways. So then these guys are done. Let's chip.
X is
This is your x-axis,
right.
and this is your y-axis. I had a really funny student one time. She's like, "Oh, Emily, I can never remember those." And so she imagines that there's a tree here that would be falling on some little guy. And he's like, "No!" It's like, I don't know. No. Crossing his arms. Like, yeah, whatever you gotta do, I guess. But can't have those on our feasible set. But that's how she remembered that this was the x-axis. No. Whatever you gotta do. All right. Let's give these different colors. That might be nice. 3, 2, 1. Let's start with 3. 3 is a gimme. Why? Because you are going to draw a line at y equals 6 and then figure out which side of the line is in the feasible set. All right. So let's do that. Y equals 6. Here we go. So this is line 3. If y has to be less than or equal to 6, then I have to be below this line, right? And when we talked about it, we said, okay, it would be tempting to shade in the area that applies, but then you need to figure out what area satisfies all of them, has the overlap of all of them, and that's difficult. So for drawing it by hand, it's potentially easier to remove all the area that doesn't apply. Okay. Which means that this would be gone already. This would be gone. Okay. Let's work on line 2. Line 2 is going to require a little bit more work, but that's okay. Or should I do 1? That seems weird. 1. 2x plus y is less than or equal to 16. If we want to draw this on here, we're going to draw a line at 2x plus y is equal to 16. If I rearrange this, it might be nice to have it in the form of y equals mx plus b, right? Rearrange in terms of y. You don't have to, though, but you could. Y is 16 minus 2x. As long as you plug in one of the values of x or y, you can choose y if you want. But for me, my go-to is plugging in x equals 0 and figuring out what y is. So here, when x is 0, y is 16. So I can draw a point there. That's 1 point on the line. And maybe I'll do 16 minus 2x to clarify here. let's pick I don't know. What's a convenient value would be x equals 8. Why? Because then I could do 16 minus 2 times 8. That's nice. Sixteen minus 2 times 8 is 0. But you could have put in any value of x. Doesn't matter. But it does make it nice to know where it crosses the x-axis. So now this is where you would take your straight edge, but this is why I would, I'm gonna give you the lines. Because I can. I should have waited for it to straighten it out. Let's see here. Nice. Two x plus y has to be less than or equal to 16. Right? And so then I'm going to be on this side of the line, right? So that means that I can draw arrows going this way. That's in my feasible set, and I can shade that, and it's out of my feasible set. Last line. 2x plus 3y is less than or equal to 24. First thing I'm going to do is I'm just going to set it equal to 24. So I don't have to deal with the inequality. So I'm just drawing the line anyways. And I am going to solve for y, even though it gets a little bit ugly. Because y is 24 minus 2x divided by 3. There's a reason for that though, because I have to find the intersections later, right? So having them both set to y already is going to pay off. Yeah. But you don't have to. You can jump straight into here and plug in some value of x and find y. Plug in some x or y and solve for the other one. But let's see here. Let's do the same thing. I have x and I have y is 24 minus 2x divided by 3. Let's go for my go-to of x equals 0. It's pretty rare that I would not use x equals 0. 24 minus 0 is 24, divided by 3 is what? The math. Is it 8? So when x is 0, y is 8. Oh, and I should label this as line number 1. Where? Sure. 12, oops. Let's just make sure, okay, yeah. The only concern would be if 12 wasn't showing here, then that would make it hard to graph. But 12's on here, so why not? This is 12, 24 minus 24, convenient values, nice. 0.
Why don't you just make y equals 0 and solve for x? I know you can say, oh, yeah, we're going to plug x into this and solve that. Why don't we just do that?
You can do it that way.
Oh, it doesn't really matter.
Yeah. No, as long as you plug one in and find what the other one is, you can work it that way. But whenever I do that, and I mean, I do it in my head where I'm like, oh, how can I make this 0? right? But because that's kind of hard to get to a little bit. So I do that, but a lot of people find it confusing if I start switching things up. But you can go from here to here.
What say you say on having to worry about defining both sides by negative numbers, flipping,
For the inequality, no, I haven't included anything like that. Yeah. Yeah, like here we can avoid it because we can just set it equal to and then go back and revisit which side of the line we would be on, right? And so you don't need to worry about it. The only other inequality is in the absolute values, but you'll see we can avoid it anyways. So. Okay, let's draw this line. Uh-huh. Good enough. Or as my husband likes to say, good enough for government work. And he's in the military, so. Those guys. Let's see here. Let's do an orange one. So if 2x plus 3y is equal to 24 is this line, and I need to be less than this line, then I exclude, or include, I should start with include here and here. And then, but most of those were already out, right? The only exclusion that's new here is this section. Right. Now what I like to do is draw kind of the feasible set I guess I could, no, I won't. Could write feasible set. But we're not done. Make you work for it. Graph the feasible set of the system of inequalities and give the coordinates of the intersections, including the x-axis and the y-axis. The easiest way to do that would be to label these intersections A, B, C, D. We could do the origin too, but we don't have to. It's optional. So the reason I've labeled these lines, right, is so that I can keep track of, okay, A is the intersection of x equals 0 and y equals 6. That one's pretty straightforward, right? B is the intersection of line 3 and line 2. C is the intersection of line 1 and line 2. And D is the intersection of y equals 0 and line 1. Right? So A, B, C, D. Some will require more work than others. A is at 0, 6. Really no work required. Oops, clean that up. B, we said, was at the intersection of 3 and 2. Which is why I like to have them in terms of y equals 6, because if I have all of them in terms of y equals, then by transitivity-ish, right, then if 6 is equal to y and y is equal to 24 minus 2x over 3, I can set those equal to each other. And I can solve for x. So if 3 is equal to 2, then that's the same as saying 6 is equal to 24 minus 2x over 3, 18 minus 24. I have my cheat sheet here. Divided by 2, I get x is equal to 3, which tells me that we know y is at 6 because that was the first line. That happens at 3, 6. And you can always confirm it. Does that look reasonable for B? It does, even though I drew it by hand. C was at the intersection of 1 and 2. So where 1 is equal to 2, so 16 minus 2x is equal to 24 minus 2x over 3. Can rearrange this thing. And you can find that x equals 6, which means when x is 6, y is 16 minus 2 times 6, putting me at 4. And we already know that D is at 8, 0. So solving systems of equations, I snuck that in there, right? This is solving systems of equations. Set them equal to each other, solve for when they are the same, when they have the same x and y values. Intersections. Nice. Then we're done. Yeah.
Where did you get the 3 square root of 1 plus 2 for B? The first part?
So 3 is equal to, for intersection B, it's where the line 3 is going to be equal to the line 2.
What about on C where it's 4?
So C, if we look at the intersection of C, right, because it's representing this intersection here. And that's the intersection of 1 and 2.
It's not 4.
Like, what? The math says, I'm sure. Nice. So finding the points of intersection, including the, because we didn't get to it, but if you have a function based off of x's and y's, it's going to be optimized at one of these vertices, right? And so we didn't get to it, but it's out there. It exists. Just a short plug in the values away. Find the equation of the line that passes through 2 points. Sounds familiar from the outline, right? What's your first thing you're going to do? You have to find the slope. M is y2 minus y1 over x2 minus x1, or however you want to find it is fine by me. You don't have to use the formula. It's rise over run. You could even plot them and look at what they would look like, right? But I've memorized the formula, so I get to use it. You can too. If I let this be x1, y1, and I let this be x2, y2, doesn't matter as long as you keep track of which one is x2 and y and kind of 0.1, 0.2. As long as you're consistent, it doesn't matter. 3 minus negative 3 divided by negative 1 minus 5. Negative 6 divided by negative 6, score. It is. Thank you. Not quite the score, but still pretty good. Just a slope of -1. Okay, that's your first part. Now, you can take that slope into y equals mx plus b, right? The equation of a line is what we're going through, or going for, I guess. So y is -1 is the slope times x plus b. We still need b, but we have 2 points, and you can pick whichever point you want, right? Because I have an xy coordinate that's supposed to be on this line, right? So I just usually go for the first one, doesn't matter. -3 is equal to -1 times 5 plus b. Then I can solve for b. -3 plus 5 tells me that b must be 2. I better, yeah. I don't have any more cheat sheets, so that's it. Now I'm on my own. So now the equation of the line is y equals -1x plus 2, or just -x if you want. Step 1, find the slope. Step 2, find the intercept using one of the points, and then put it all together. Why are the next 2 questions the same? Oh, and if you grabbed the practice test last night, I had a little copy pasta incident where this still said parallel, so it was two parallel ones. That's not very good. I meant perpendicular here, so just make sure whatever one you're working with, the ones I printed say perpendicular, but little miss. That's okay. Why are these questions both the same as the previous question, essentially? First thing, you need to find the slope of the new line. And so find the equation of the line parallel to y equals -4x plus 10, passing through this point. So how can you get the slope? Well, that tells me that if they're parallel, then m1 is equal to m2, right? So m must be -4. From here, knowing that this new line has to pass through this point of 0.51, then you can pick up basically at this point, right? Because now you know you have a slope of -4 and you can solve for the intercept, and then you've got your new line, right? Because I'm worried about time, let's see here. I'll leave it there. I'll post the solutions, of course. What does it mean to be perpendicular? One of the ones you have to memorize. M2 is -1 over M1, or M1 times M2 is -1 if you prefer. But this way you can kind of just go for it, which tells me that the slope of the perpendicular line would be -1 over 5. And then you're back to the same spot. Right? You have the slope, you have a point that has to be on the line, you can use that to find the intercept, and then you've got the line. Nice. How about the absolute value function? It was a piecewise function, right? The absolute value, we know it turns negative values positive, but how? Well, we've got it in our notes, but for us to be able to solve this, we look at the inside. So 2x minus 1 can be 11. The absolute value of 11 is 11. Okay. But -2x minus 1, right? The negative of this thing can also be 11. Or if you prefer, but for some reason, I always put the negative on this, on the inside function. There's no harm really in moving this negative over here. So you could say 2x minus 1 is equal to negative 11 if you prefer, and solve it that way, right? But I just like the symmetry of the positive inside and then the negative inside, but it's up to you. Then solving 2x minus 1 is equal to 11. I get 2x is 12, so x must be 6. And then I can do negative 2x plus 1 is equal to 11. See how, so I don't know why I don't use this one because it's easier. But for some reason I hesitate to, but you get the same answer, so it doesn't matter. Need to see how far, oh boy. I get negative 2x is 10. So x must be negative 5. So just pay attention, you're gonna have 2 answers for the absolute value. Why is the next one the same type of question? Yeah, that's how marks work, I think. What's the horizontal intercept? The horizontal intercept is where it crosses the x-axis, which means that y, or f of x, is equal to y is equal to 0. Kind of implied knowledge that you would need. So what you're solving is 2 times the absolute value of x minus 3 minus 2 is equal to 0. But just like exponential functions and logarithmic functions, we need to isolate the absolute value before we can apply our kind of split method. So I get 2 times the absolute value of x minus 3 is equal to 2. So the absolute value of x minus 3 is equal to 1. Now I can split it, right? I think of it as splitting. I'm not actually splitting it. I'm considering both of the options, where x minus 3 is equal to 1, which means x is 4, and where negative x minus 3 is equal to 1, negative x plus 3 is equal to 1, which means x is 1 minus 3, but then the negative, putting it. Or you could do x minus 3 is equal to negative 1. And you would get to the same spot. Right. But I like the symmetry. I think it's from the piecewise definition of the absolute value. How about an absolute value inequality? Kick it up a notch. We want to find where the absolute value of x minus 2 is greater than 9. Now, if you remember your absolute value functions, right, it's this b, and it's facing up, I can see, because I don't have a negative up front, but it's been shifted over to the right by 2, and I want to know where it's less than 9, so cut off here. Knowing the anatomy of the absolute value function would tell me where the solutions are, but we don't need it. So how do we do it? Well, we can figure out, so kind of background knowledge. This function, this absolute value function, looks like this. Right? It's been moved over to the right by 2, and here at 9, we want to know where it's greater than 9. Okay, phew. Like, no, I don't remember that. There, greater than 9. So what can we do when we live in a shoe? We can set it equal to 9. So step number 1, but I'll make this kind of dreamy to show you that you don't actually need that knowledge. It's helpful, but you don't need it, right? And this would be at 2. Because you can set x minus 2 is equal to 9. Now it's not allowed to be 9, but we can find these intersections, right? Is what we're doing when we're setting them equal to 9. We can do that. That means that x minus 2 is equal to 9. So x is 11, or negative x minus 2 is equal to 9, which means negative x plus 2 is equal to 9. So x is negative 7. That's where a transition is going to happen, right? From being less than 9 to being greater than 9, right? One way or another. So what we do is we can, pick some test points, negative 7 and 11. That's where it's equal to 9. Yeah. We already know that our answer will not include these points, but the answer is either going to be from here to here, and from here to here, or between these two, right? Because there's going to be a transition. Now, what we do is pick a value less than negative 7. Let's do negative 10. Any value, right? Then you can check the absolute value of x minus 2 is the absolute value of negative 10 minus 2. Negative 10 minus 2 absolute value is 12. 12 is greater than 9. So we're good. So that's part of the solution. You could stop here because if you remember the anatomy of the absolute value function, but I'll keep going for completeness. So that means that all the way to negative infinity, that applies. If I'm going from a negative to a positive, I always go for 0. I can't help it. Because the absolute value of 0 minus 2 is 2, which is not less than 9, so it's out. Oh, sorry, greater than 9. It is less than 9. Another test point, we could pick 12. The test points don't matter. They're going to be the same in those regions. And so we get 12 minus 2 is 10, which is greater than 9, which means it's in the region. As an interval, throwing in some interval notation from way back when, this would look like what? Negative infinity up to negative 7, not including 7, and I'm going to be looking for that, right? Because it has to be greater than 9, and at negative 7, it is 9. Right? Union. And then picking up at 11 and running it to infinity. Ta-da! We did it. Okay. Are you going to watch me do matrix algebra? I don't know. How about I just post the solutions for this one? Just me reading out pivoting, mostly because I'm concerned. I gave you a lot of solving the linear systems. I'm not going to give you this many. I'll make you do 1, but I gave you 3 for practice. So well, I guess I gave you 4, sort of. One's a little different, but there'll be 2 of those, not all 4. But this is harder, so I think we should do this one. Right. If you have these 4 matrices, first thing you'll want to do is figure out the order of the matrix, right? And so usually what I'll do is I'll jot down below here, this is a 3x2 matrix. B is also a 3x2 matrix. So they have the same order and the same size. C is a 2x3 matrix. And D is a 3x3 matrix. We need those orders to figure out if we can add matrices or multiply matrices or find the inverse of a matrix, right? You could practice. Can you add A and B? Yes, because they have the same size, right? And so A and B, you can add those. Can you add A and C? No, because they have to have the same size, because adding takes just the element and adds it to the matching element. And that's how adding works. Okay. I will add those in, but how about 2 times C? Does it exist? It exists. It's just every element in C just being multiplied by 2. Fair enough. In fact, 2A exists, 2B exists, 2C exists, and 2D exists. Right? Any scalar multiplication just applies. Does, oh, sorry.
Would there be any case where like 2 matrices wouldn't?
Where A plus B, for example,
But if
or
it was 2C, like would there be any case where that?
no, just anything goes. Any size matrix can be scalar multiplied, which is really nice. How about A times B? First, we need to look at the orders of A and B. So A has a 3x2 and B is a 3x2, but the insides don't match, right? And so here, we're gonna say no, doesn't exist, does not exist, since the order of A is 3x2, which can only be multiplied by a 2 by n matrix. Right, the 2 and the 2 have to match up, creating a 3 by n matrix in the process. So we decided AB does not exist. Does AC exist? 3x2 times a 2x3, yes, and it's going to make a 3x3 matrix. And I think for practice, we should do it. Ah, I know, right? A times C. What are you gonna do? A times C. It does. And I've got a 3x2 times a 2x3, so my result is going to be a 3x3 matrix. I'm gonna make room. How does it work? Take the first row and overlay it with the first column, and then add those multiplied together, right? And so I will write out just the first entry here. But then I will not write out any more because it would be 4 times 1 plus -2 times 4, which is 4 minus 8 is -4. That's one of the 3 by 3 entries. Then, to make the next entry, keep the same row. You want to be in the same row, but you want the next column. 4 times 3 is 12 plus -2 times 0 makes 12. Four times -2 is -8 plus -2 times -1 makes 2 times 1 is 2. 8 plus 2 is 10. Negatives strike again. Sorry, guys. Yes. -8 plus 2 is -6. I didn't write it, so I don't have to write it in red. I think those are the rules. Thank you. Nice. Then oops, you go to the next row and do it all over again 6 more times. But try it for practice. I'll fill it in. But we are short on time. Does B inverse exist? No, right? Can only find the inverse of a square matrix. Okay. And so B inverse does not exist. Can only find the inverse of a square matrix, a square n by n matrix. So by that, I can't find the inverse of A, I can't find the inverse of B, I can't find the inverse of C, but I can find the inverse of D. Which, surprise, surprise, is the next question. How would you solve this? To find the inverse, 1, 0, 0, 0, 1, 0, 0, 0, 1, and you're gonna morph it, and there's definitely not enough room to do it, right? Finding the inverse? Yeah. It's a good way to not have you do a question like this, right? Because they're the same. You're just doing row operations on an augmented matrix. And so we've kind of outgrown this if I test you finding the inverse instead, because they're doing the same thing. Now it's all practice. There's more practice questions than the actual length of the test. Well, I'm gonna put something like this on there. Obviously. But you need to be able to find the inverse. But the inverse is just building on those row operations, because then you're gonna morph this, do whatever you need to do to turn this into the identity matrix, and then the result is the inverse. And 1, 0, 0. Or I'll say this is D inverse. I'll add add it in. So you can check your work. 2 by 2 inverses? Yeah, then you can use the determinant, but you'd have to memorize the determinant because I don't give it to you. But it still works this way. This way will always work, as long as it's a square matrix. Given a directed graph of a relation, right, the adjacency matrix, this could be kind of constructed in a variety of ways, right? I could have given you the adjacency matrix and asked you to draw the digraph, or I can give you the relation and you have to construct the adjacency matrix or draw the digraph, that kind of thing. I could ask you to look at the graph and write out the relation, which would look like what? Is the set, let's start with the ones. 1 goes to 2 and 1 goes to 3. 3 goes to 2 and 3 goes to 4 and 4 goes to 3. That's boring. The adjacency matrix of this thing is going to be a 4 by 4 matrix. Why 4? Because it has to have each of these nodes, right? And we can come from one, or in this case, we can't come to one, but in theory we could. And so 1, 2, 3, 4. And then up here, 1, 2, 3, 4. If there's natural ordering, you should use that natural ordering for your rows and your columns. So 1 goes to 2, so it gets a 1. 1 goes to 3, so it gets a 1, and the others get zeros because they're not happening. 2 doesn't go anywhere, and so it gets 0, 0, 0, 0. 3 is a little busybody. 3 is going to 2, and 3 is going to 4, but not 1 and not 3. And 4 is going to 3. Is it symmetric? Is it anti-symmetric? Or is it neither? Explain your answer. Ooh. With a graph, that makes it easier, right? It's not symmetric because then each of these, let's see here. For the symmetric, we would need 2 to 3, we would need 3 to 1, and we would need 2 to 1. Then it would be symmetric. So it's not symmetric. How about anti-symmetric? Oops. We would need to remove one of these, because you can't have a flight in both. There are words, and when I post the solutions, I'll include all the words too, but it's nice to see the visual. Is it reflexive? No, because, hey, there's not a single self loop on here. In order to be reflexive, if it would need, no, that's transitive. That's too hard for, still. We would need a self loop, a self loop, a self loop, and a self loop. All those would be missing. So I'm not gonna use the wording, find the closure of the, for it to be reflexive, for example, but the closure would be these original relations as well as the ones that are missing.
And it would be the adjacency of each one.
Totally. Is it transitive? This is where when it's asking if it's transitive, it's just, you can look at it and you can see if there's anything missing. Usually we would need something like, okay, if you can find one scenario where you can get from a point through another point to another point, but you can't get there directly, it's not transitive. So I can get from 1 to 3 to 4, but I can't go straight from 1 to 4. And therefore, it is not transitive. Is it a partial ordering, an equivalence relation, or neither? You can pick any one of these. You don't really need to remember what those are in order to answer this question, but it might be nice to remember what they are in general, which I outlined on that first page. Partial ordering, is that the antisymmetric or the symmetric one? It's reflexive and transitive for both, and then one or the other. I think it's antisymmetric. But I don't have it. Oh, I didn't write it down on here anyways.
If we only had 1, 2, and 3, it still wouldn't be transitive, right? Like, if we just removed 4 entirely. And it's grouping 1, 2. So,
Yeah, so if we remove this whole scenario, that whole mess, then it would be transitive. Oh no, no, because you can go from,
oh,
I would need to do the matrix in order to confirm. How would you do the matrix? We could use the matrix R if we ditch this guy. Then you would have 1, 2, 3, 1, 2, 3. We've got a 1 to 2 and a 1 to 3, 0. 2 goes nowhere. And 3 goes to 2. You would find R squared. Take this times itself. You would find R to the 3. Boolean arithmetic, right? Boolean multiplication is easy, right? And then you would find R plus R squared plus R to the 3. Oops. As soon as there's a 1 in there, in any spot, it becomes a 1, right? By Boolean addition. Then, if that's the same as this, which I don't know, I'd have to do the math, then it would be transitive, right? If there's no value add to adding these. So kind of curious, throw that on there. But the closure, that's the original relation and the relations needed to make it reflexive. Holy. And then I gave you another version of the question. There's only gonna be one kind of relations question, but I wanted you to see two different types of relations questions, just so you kind of have it under control. But they're doing the same thing. So I'm out of time. Well, I'm preparing you for both, aren't I? I think it might be nice to either do a function composition like this, because then you could use your matrix multiplication if you wanted to. I think that's the easiest thing. But I do want to incorporate something like this. So might be nice. Test that Boolean arithmetic. I am way over time, but if you have any questions, let me know. Stick around, but if you have to go, I understand. It is Friday night after all. Have a great weekend, and I'll see you on Monday.